In this video, we're going to have a look at how we can tackle conjecture-styled questions in a trigonometric context. So question 1, given the following models, 0 equals cos x plus 1, 0 equals cos 2x plus 1, and 0 equals cos x over 2 plus 1, using your method of choice, find the values of x that satisfy the above equations. So simply what's been asked here is solve for x. And notice that the domain in this particular question is completely unconstrained. So we're going to get multiple solutions. So to solve for x for the first model, we're simply going to go 0 equals cos of x plus 1, rearrange. So negative 1 goes on the left, then cos of x. And then we're going to take the inverse cosine of both functions, like so. Now, looking at the unit circle, because we always should draw a unit circle when we're tackling these particular problems, we're going to find that we expect our solutions for this problem. So usually with cosine, we're expecting in here and here for positive. But recall we're looking for negative 1, so usually we go here and here. But we're not going to be getting two solutions for this problem, because notice the value is negative 1. So when the value of, or the output of cosine is negative 1, we're actually sitting on the boundary between quadrants 2 and 3. So this location here. So this is negative 1, 0 on the unit circle, and it's at pi radians. So what we're going to find is that in this instance, x equals pi. Now, you may go ahead and simply say, we're done, we've solved it, we've got the answers, but remember, the periodic nature of the trig functions and the fact that this question has a completely unconstrained domain means that we're expecting infinite solutions. So what we'll do is we would write plus 2k pi, and then we would state where k is an integer. Therefore, we've found a model of x which would satisfy the equation above for all values that x could be, so over an infinite domain. So this would be our first solution, or this would be our solution to the first model here. Now going to the second model, we're going to go 0 equals cosine 2x plus 1, rearranging to solve. Negative 1 equals cosine of 2x, and then rearranging again, taking the inverse cosine function, we're going to get inverse cosine equals, or 2x equals the inverse cosine of negative 1. And I'm not going to do the unit circle again because the one we have on the left is completely adequate. But what we'll find is that 2x is equal to pi. And remember the periodic nature of cosine. So it's not just going to be pi, it's going to be plus 2k pi. And once again, k is going to be, there we go, k is going to be an integer. But we're not done quite yet, because this is 2x equals pi plus 2k pi. What we need to do is find it in terms of x. So we can go 1 over 2 pi plus 2k pi. And we'll leave it at that. So this would be the values of x that satisfy the equation for model 2. Now for model 3, 0 equals cosine of x over 2 plus 1, rearranging, negative 1 equals cosine x over 2, taking the inverse cosine once again, we're going to get inverse cosine of negative 1, and using the unit circle on the far left, x over 2 is equal to pi, and then we remember to go plus 2k pi because we're looking for all solutions and it is infinite. So rewriting, where k is an integer, then we can say we can say we want the value of x, not x over 2. So we go x equals 2 pi plus 2k pi. And that would be an adequate solution for model 3. So we've found all of the values of x that satisfy each of the equations up here. Now, part B, make a conjecture about the possible solutions for x in the following model. 0 equals cos nx plus 1. Well, firstly, let's think about it. What is this n? What is it? Well, it's the period dilation factor. Now, what does it do? Well, it's going to increase so for high values of n, what it does is it decreases the period of this cosine function, and for low values of n, so values that are less than 1, it increases the period. Now, going up to here, notice in question 1, there is no period dilation factor, or there is, but it's just set to a value of 1. And what we see is that our value for x is pi plus 2k pi, which is exactly where we expect to see it on the unit circle. Now, going across to model 2, we've got a period dilation factor of positive 2. And going down, what we see is that the difference between model 1 and model 2 is there's a scaling factor on the values of x of a half. Now, going across to model 3, we've got a period dilation factor of 1 over 2. And the values of x at the end, they're scaled by a factor of 2. So, what you can see is that, if we're going to form a conjecture, we could say that the period dilation factor impacts the values of x that satisfy the equations of this form, to be specific. And going up, you can see that the period dilation factor, in this case n down here, it scales the values of x as a factor of 1 over n. So you could write the values of x are scaled by a factor of 1 over n. So what we've got here is our conjecture. In the first sentence, we've gone for a really vague or very general statement and say that the period dilation factor affects the values of x. And then for the second sentence, we've gone in for the striking blow, and we've said the values of x are scaled by a factor of 1 over n. So this would be an informed opinion about what we believe is going to occur when we have this particular model up here. So what the values of x will be for this particular model. So remember, for conjecture questions, a conjecture is a mathematical statement that has yet to be rigorously proved. Now, it wouldn't be a real question if we didn't try and prove the conjecture that we stated up here. So, in part C, it says, prove your conjecture algebraically. And the way in which we can do this is business as usual. So exactly what we did in part 1. So we simply write out the equation, and we're going to solve for x, ignoring the fact that there's an n there. So we'll go -1 equals cosine of nx. And then we'll take the inverse cosine from both sides, and that will leave us with n times x. And then the inverse cosine of 1. Now, what we could do is we could have an interim variable, so we could say like let theta equals nx, or we can just assume that these come as like a package deal and we'll keep them together. So what we find is the values of n times x is going to be pi radians, and then we're going to throw in the plus 2k pi. And then we need to be explicit about what this k is, and we'll say where k is an integer. So k is not going to be a half. It's not going to be a root of, say, like square root of 5 or a cube root of 7. It is going to be an integer, so 0, 1, 2, 3, or 0, -1, -2, -3. It's going to be a whole number, either positive or negative, and therefore it is general enough to collect all of the possible solutions for n times x. Now remember, we're solving for x in this case, so we're going to go x equals and divide everything through by n. And what we'll find is that we get to the bottom of this problem, and it becomes 1 over n times pi plus 2k pi. So our general solution for a model like this is, we'd say x equals 1 over n times pi plus 2k pi. So what we find is the period dilation factor impacts the values of x that satisfy the above equations of this form. So the period dilation factor impacts the values of x. So does that statement hold up here? Does the values of n impact the values of x? And what you can see is the value of n does indeed impact the value of x. Now, second sentence, the values of x are scaled by a factor of 1 over n. Boom. So if we go down, the values of x are indeed scaled by a factor of 1 over n. So what we've done is, in part A, we sort of gained some data, or we solved some problems to give us some data. And then in part B, we were given a model and we explained what we would expect to happen based on what we saw above. And then in part C, we demonstrated that our conjecture here is in fact true. So this is how you would approach a conjecture styled question that is based on a trigonometric background.